Welcome back to the NPTEL online certification course on microelectronics devices circuits. In our previous lecture we had understood the basic structure and the doping profile of BJT. We have also understood two types of BJT which is available to us. One is known as NPN, another is known as PNP. In the first case, which is NPN, electron is the majority current carriers. In the second case, hole are the majority current carriers. What we will learn in this module or in this lecture is the working principles of BJT, right, and we will see why is it therefore termed as a bipolar technology. Let us maybe it will be easy if we start with an NPN transistor and then we can take up the case of a PNP transistor. So, before we move forward and we discussed about NPN and PNP transistors, let's just recapitulate what we know about a PN junction or a PN junction diode or simple PN junction, right. So, if you have a P type material and N type material here and you do not apply any bias, let us suppose the bias is 0. So, I am just keeping it open circuit here. So, VB is equals to 0, then what will happen is that free electrons from here will be jumping to this place, they will be diffusing, right, because there will be diffusion at this place. Why there will be diffusion? Because you have a large free electron concentration here and you have got very low free electron concentration here. Therefore, electrons will be jumping from N side to P side. As a result, what will happen is on the N side you will be left with what? Positive ions which are nothing but your donor species. And what happens on the P side? These electrons will recombine with holes and you will have negative charges, effective negative charges will be available to you, right. So, what is the big picture therefore, that even if you do not apply any bias, because of a diffusion between P type and N type material, you will have a region near its junction. This is known as metallurgical junction, right. Please understand, this is known as a metallurgical junction. This junction, PN junction is basically known as a metallurgical junction. If you look at this junction, so initially therefore what will happen is that electrons will be moving and this side you will have fixed charges which are positive in nature and you will have fixed charges which are negative in nature. Why? Because electrons have left from the negative side, as they went they left behind their donor atoms there and therefore you will have this positive charge. So, what happens is that there will be electric field which will be directed from N side to P side inside this region, right. First of all, therefore, this region which you see, this region is referred to as the depletion region, fine. So, this is the depletion region. So, why it is known as a depletion region? Because this is the region which is basically depleted of any free charge carriers. So, please understand, there are charges, but these are not fixed, these are not free charges, they are fixed charges, right. Why fixed charges? Because electrons have left their position leaving the donor atoms, ionized donor atom. So, if I have a donor atom Nd, right, it gives one electron and it converts itself to Nd plus, right. Accepted atom, right, gives one holes there and becomes a negative atom available to us. Now, so the idea therefore is that since this is, and therefore this region which you see in front of you, this region is primarily devoid of any free charge carriers and therefore it is known as the depletion region, which means that under 0, even under 0 bias condition, the PN junction is basically having a depletion width which is W, let us suppose, right. This will always be there, you like it or not, even at 0 bias there will be the junction will be deployed or devoid of any free charge carriers. Now, why after sometimes this movement stops for free electron from N type to P type? See, so what is happening is therefore for electron to move from N type material to P type material, now it has to cross this depletion region, agreed. But just as it enters this depletion region, it sees an electric field which is directed this side, which means that, because if you remember it is minus E into E, right, negative Y mine, because electron is a negative charge, therefore the force on the electron is minus E into E and therefore electron trying to enter this side will be pushed back on this side, right. So, beyond a particular time when the electric field becomes so large that any extra electron coming from n type and trying to enter into the depletion width to go towards the p side will be pushed by the electric field within the depletion region and force it to move outside the depletion region and throw it towards the n side. So, what is the overall picture therefore what we get? That overall picture therefore is under 0 bias condition there will be a fixed width of a p-n junction and that fixed width is basically my depletion width W, right, and therefore this will be devoid of any, this part will be devoid of any free charge carriers, right, if this is a p-n junction diode and we have not applied a bias here. Now, let us see what will happen if we forward bias this p-n junction. As we very well know, forward bias basically means that the p type is connected to a positive terminal and the n type is connected to negative terminal, right. Let us look from the n type material. Now, what will happen is that, or from the p type material, either way you can have a look from the p type material. So, if you have a positive polarity battery connected to the p type material here, the holes which are majority current carriers here will see an electric field in this direction because this is positive and this is negative. So, there will be electric field. So, these holes will be pushed towards this region, right, will be pushed. Similarly, electrons will be pushed in this region, right, they will be pushed near the depletion edge. As it enters, so please understand, within the depletion region the electric field is in this direction. So, I will make the highlighter pen slightly change the color so that you are able to appreciate what I am trying to say. The electric field within the depletion region is in this direction, whereas outside it is this one, right, this is the direction. Therefore, once a hole enters a depletion region, let us suppose this is the hole, it enters the depletion region by virtue of this electric field, it will be again thrown, it will be at least these electric fields which are marked in blue will try to throw the hole towards the p side and any electron entering from n side will be thrown towards n side. But now please understand, you have an external bias which is say VBE, let us suppose base emitter or whatever VBE or VXE whatever, which will help the holes and electrons to cross this barrier, right. So if I am able to see that, so extra electrons will be crossing this barrier or extra holes will be crossing this barrier, and once it reaches on this side, right, it tries to remove some of the electrons available here, and therefore what happens, similarly electrons moving from this side to this side as it starts to move, the depletion width actually therefore starts to reduce, right. So, as you make the p-n junction more and more forward bias, your depletion width starts to become lower and lower. This can be also understood in this manner. So, if you look at depletion width, it primarily means that the holes has to acquire an extra energy to cross this barrier. So, for an hole it is basically a barrier, right. So, if you are able to provide a bias which is BBE, what it happens to the hole is that it lowers the effective barrier drastically. So, this was the initial barrier length, now this becomes the initial barrier. Now, it is easier for holes to cross the barrier, right. So, we should look at it in this manner. So, we come to one major conclusion out of it is that when your p-n junction is forward biased, right, the depletion width will reduce. A time might come when the depletion width will go to 0 and you will have some current flowing because of the external bias for VB not equals to 0. So, there will be some current not equals to 0 for VB not equals to 0. This is the condition when you do a forward, this is known as forward bias. Now, let us look at the fact what will happen if you go to reverse bias, which means that you just convert this whole thing and maybe the next I can help in this slide, that let me say I have this and I have got this, I have Pn, I had a depletion region already formed. Now, I had connect p type to a negative side and n side to a positive side. So, I just reverse the polarity of the battery, right. Now, I leave an exercise to you to and you can easily appreciate what will happen now is that this depletion width which was initially this to this will now become larger, the new value of depletion width will be this one, which means that under reverse bias condition the depletion width increases, right, and as a result the current will be further lowered or there will be no current flow. So, please understand therefore, from a basic study of p-n junction diode theory or p-n junction theory, when you forward bias a junction, more is the current, when you reverse bias a junction, less is the current. Why? Because the forward bias will give you a lower depletion width, a reverse bias will give you a higher depletion width. With this knowledge you have gained as far as a simple p-n junction is there. Let me come back to NPN transistor and explain to you how a NPN transistor works. So, look at the fact, let us remember our previous lectures basic principles, that the emitter will have a very heavily doped, and that your holes will your base will be relatively very less doped, it will be very thin also, and your collector will be relatively less doped, but it will be same doping as that of the emitter. So, this is an NPN. If you look very carefully, this is N type semiconductor, this is again an N type semiconductor, and this P type semiconductor. What we have done is we have forward biased the base emitter junction, and what we have also done is we have reversed bias the base collector junction, right. This is just for information at this stage. This is also known as the active mode of operation. We will discuss that in subsequent slides, but just to give you a functionality of this NPN transistor, we forward bias the base emitter and reverse bias the base collector and see how the current flows. If you look very carefully, therefore, when you forward bias the base emitter junction, right, you reduce the depletion width on the base emitter junction region, as we discussed just now, just a few minutes back, right, and you reduce it. When you reduce it, you force large number of electrons from the emitter side, right, and they will be injected onto the base side. So, this is the injected electron which is flowing, right, because you have forward biased N and P junction here, right. As it enters the base region, this is where the critical aspect of a bipolar technology works, or bipolar junction transistor works. As it enters the depletion region here, right, please understand the base region is typically having very small number of holes, because it is slowly doped and it is very thin. So, what will happen is majority of the electrons will actually cross the base very fast, because it is very high velocity, but some of the electrons will actually combine with some of the holes present here. So, there will be an electron hole recombination, right, and there will be so the holes will be lost, because electrons will eat into the holes, and as the holes will be lost, right. In order to make the same number of holes as it was previously, you see there will be a current which is known as IB, which will be flowing into the base. So, please understand these blue colored current sources which we are showing to you is basically the conventional current, these are not electronic current, right. So, therefore, if you look at the base here, which is this one, if you look at the base here, then in the base the direction of the current is basically into the base, and the reason why is it into the base is that the holes are now. So, let us suppose 10 electrons recombined with 10 holes. So, 10 holes were lost. In order to therefore make again the 10 holes available to me, 10 holes from the base side which is being fed by VBE. What VBE? This VBE will enter into the base side, and therefore, the blue colored arrow is going inside the base, right, and this is the base current, very small current. Because why base current is very small? Because the number of holes are very small, right. So, the probability of recombination is also very small, and therefore, I would not expect large base current to be available to me. Now, what has happened therefore is those electrons which did not recombine, they went and towards the base collector junction. But please understand, base collector was reversed bias, right. So, what does when the electron comes here, what does it sees? It sees a negative potential here, sorry, it sees a positive potential here, I am sorry, because of this VCB, and therefore, they will rush through the depletion region, right, and go towards the collector side. if there would not have been any positive charge here or positive potential here, electron could not have crossed the base collector barrier, because base collector barrier, please understand, is large as compared to base emitter, because it is reverse bias, right. So, if there would not have been any positive potential near the collector end, I would not expect it to see the electrons to cross the barrier, because you are not providing that much amount of energy to electrons to cross the barrier, and as a result what will happen, electron would not flow. But since you have provided a VCB, a very large potential as compared to VBE, and that too reverse bias in the base collector, the electrons will see a very large potential on the collector side, and as a result what will happen, it will force itself through the depletion region and reach the collector side, right. And as a result there will be collector current. As you can see, it is again pointing inwards. Why pointing inwards? You very well understand why is it pointing inwards, because electrons are moving outwards, therefore whole current is moving inwards. So, I have IB inwards, IC inwards, and IE also moving outwards, right, IE outwards, because electron current is moving inwards, right. So, this is what basic structure of base current looks, or the basic idea looks like. Now, if you look at another issue here, which is quite an interesting issue, is that when you apply a VBE base emitter, you are basically forward biasing this base emitter junction, right, base emitter junction, you are forward biasing it. Now when you are forward biasing it, you are also reducing the width of the emitter base junction layer, as we have already discussed this point. So, just as it is easier for electron to move towards the base side, it is also easy for the holes to move from base to towards end side. So, you see, you will also have one current contribution because of injected hole from the base side, right. So, you have injected electrons, this is primarily diffusion, and then you have drift, and these are injected holes from base towards the collector side. However, as IB1 will be very small, because as I discussed with you, small base current is there, and therefore IB1 will be relatively very small, which is there with you, right. So, I have 3 currents therefore, IE which is here, right, IB and IC, and therefore by Kirchhoff's current law, IE will be equals to IB plus IC, right, and obviously VCB should be much larger than VBE, fine. And this is the basic fundamental working, that which means that if 100 electrons started from emitter, then maybe 90 electrons reached towards the collector, 10 were recombined on the base, and therefore by changing the biasing of the base emitter junction, I can change the total amount of current flowing through the collector side, right. I can also therefore change the collector current by changing the base current, because I equals to IB plus IC. So, if I want to make IC larger, I reduce my IB, because IE is fixed, right. So, changing one current by or getting the final current high or low by changing one of the parameters of the other current is the prime example of a BJT, right. So, this is the basic example of a BJT which I just wanted to give you an idea. The same concept, the same thing, exactly the same thing can be applied to holes also. Only in this case the biasing of the battery will change, and this is therefore forward biasing it because it is P and N type, and this is VBC, again reverse biasing it. Understanding part is exactly the same as the previous case. So, I am not going to details of this, you please work it out yourself from the book, or you can yourself do it. It is pretty easy and pretty simple to understand. The concept remains the same, that base emitter will be still forward biased, depletion width will be small, base collector will be reversed biased, it will be still large, and so on and so forth. In this case, since the base is made up of N type material, the recombination on the base side will be relatively small, and therefore the base current will be relatively very small, right. And as in the second case, as you increase the value of VBC or VEB, you will actually able to control the current flowing through the collector side. So, these are the few important aspects which one should be able to handle as far as this is concerned. Now, therefore, the various modes of operations are given as these are the various modes of operation, right, depending upon the bias condition, very simple, straightforward. How you so there are two biases, right. So, I can have 2 to the power 2, so I can have 4 sort of modes, right. Is it okay? Why? because there are two bias conditions, right, and I can therefore have and each one of them can be reversed, right, because why, two biases, two battery sources, and each battery source can be either forward biased or reversed biased. So I can have therefore 4 conditions available to me: forward forward, forward reverse, right, reverse reverse and reverse forward. So each one of them will give rise to each methodology. We will come to it one by one and we will see how it works out. I think you can appreciate these points. The first thing is, if both emitter base junction, this is EBJ and CBJ is the collector base junction. So if EBJ is reversed and CBJ is reversed, then of course you can understand it will be cut off. Why? Why it will be cut off? The reason being, if both are reversed bias, then emitter base junction depletion width is also very large, right, and collector base junction width is also very large, both the widths are very large. So there is no question or no probability of any electron coming from the emitter side and entering into the base side, right, and therefore there will be very small current or almost 0 current in the region, right. Then we define that to be as a cutoff, right. Why cutoff? Because you are applying a bias but you are not getting any output current, then we define that to be as the cutoff mode of operation. I just missed one small point in the previous discussion, which I will just take care of it by this understanding, and that is something like this. See, in an n-type semiconductor which you see in front of you, this one n-type, electrons are the majority carriers, right, this we have already seen, majority carriers, but we forgot one small thing, that the holes are also there, but these are minority, very small in numbers. So on the emitter side you will have electrons as well as holes. Electrons will be very large in number, and therefore we were discussing the current flow in a BJT from electron point of view, but there will be also holes available here, please keep this in mind. But for example, in this case for if even if there are a few holes inside this n-type semiconductor and you forward bias this emitter base junction which is available, please understand, for a minority current carrier it will not be a hill but a slope. Why it will be a slope? Because this is emitter base junction. So if it is an N, it's basically a PN junction, no, it is an N and P. So this is therefore the electric field will be, so if these are electrons, electron will move this side and the electric field will be directed in this direction. So any hole which entered somehow or other in the depletion region can be dragged. So for hole it is not a big hump, for hole it is basically a small slope. Similarly, electron on this side will be also a small slope as you move. So please understand, though majority current carriers do not contribute to the current when both are cut off, which means that when both VBE and VCB are reversed biased, RB, then we define it to be cut off. But please understand, this is by virtue of the fact why we cut off, because majority current carriers are very low or almost 0. But please understand, there might be a current because of the minority current carrier, because for minority current carrier it is not a hump but it is not a hill but a hump going downwards, right. But since that current is very low, maybe 10 or 100 orders lower than the actual current. So if you have milliampere current flowing for the forward bias or on current, this might be the order of microampere or much smaller than that, we generally neglect that current and say that okay, the device is off. But please keep in mind that as a second order effect you generally have these currents which are there with us by virtue of minority current carriers, they are always there, right, and that makes our life slightly difficult. So we have understood cutoff. So cutoff is what? When both my emitter base as well as collector base junctions are reverse biased, and you therefore understand why they are reverse biased. The second is basically my active mode of operation, and this is the most actively used mode of operation, generally used in amplifiers to a larger extent, where your emitter base junction is forward biased but your base collector junction is reverse biased. Please understand the idea behind it. When you have emitter base junction forward biased, you are allowing larger number of emitter atoms, which is electrons, emitter free charge carriers, to enter into the base region and collector region, right. So currents are very large. So and when you reverse bias the base collector region, you actually allow large amount of, you allow acceptance of large number of electrons from the emitter side, right. So, therefore, in the active region emitter base is always forward biased and collector base is always reverse biased, right. Let us look at reverse active. Reverse active is when you just reverse these two. That means your emitter base junction is now forward biased and your collector base junction is now your emitter base junction is now reverse biased, which means that you do not allow large number of emitter currents to flow, but then you make your forward biased collector base junction, right. The last one is saturation, and that in which case both emitter as well as collector are forward biased. In this case you have a large amount of current which flows through because both your collector base junction and emitter base junctions are forward biased. As a result you allow a large amount of current to flow. So, there are 4 modes of operation. In general we will as we move off we will see that I can use transistor as a switch, right, wherein I can move from cutoff to active to saturation. I can also use transistor as an amplifier when I move from active to reverse active and so on and so forth. So, just by varying the biases, right, applied biases, I can let it work sometime as a switch from on to off state and vice versa, and I can let it also work as an amplifier. So, we will see as we move along what these operations are and how this operation looks like, right. We will not go into details of this one, but I will give you a brief idea about where we are at this stage. Now, as I was discussing with you that there will be always minority current carriers which will be there apart from the majority current carriers in a particular region. Now, if you look at this plot which you see in front of you, this plot, this is basically a profile of the minority carrier concentration in the base and the emitter of an NPN transistor. So, this is my emitter side, right. This is my emitter base depletion junction, this is the emitter base depletion junction, this is my base region, and then this is my collector base depletion junction here. Now, so your NPN transistor, so the base is basically p type, right. So, what does the graph show is that in ideal condition the electrons concentration, which electron is basically a minority current carrier on the base side, will fall linearly from NP0. NP0, if you look very carefully, NP0 means electrons on the p side at 0 means this is 0, this is 0. So, from there it will be maximum because it is nearest to the emitter side, and then it will fall to 0 near the base at the emitter side. Why? Because at the collector side all the electrons are pulled by virtue of the reverse bias of the base collector junction. So, at the emitter side you have large number of minority current carriers because electrons are being fed from the emitter side. So, your NP0 is typically very high, but as you move towards the collector side, since collector is drawing all the electrons away from it, I would expect to see per unit volume electron available there to be relatively very low, right. So, that is the reason we see a linear, almost a straight line drop of electron concentration from a very high value to almost 0 value near the near this thing. But we will not go into details of it, but with recombination, because actually this is with the assumption there is no recombination. If there is a recombination, it is almost a parabolic sort of a non-linear profile which you see in front of you. Not at this stage, not very important from the point of view of understanding the physics of the device, but please understand 2 things, that the doping concentration of my minority current carrier in the base region is a function of my width, effective base width, and so on and so forth. So, this is what the effective base width looks like. Maybe in the next turn when we come back we will discuss about the various concentration, electron diffusion current, and so on and so forth. What we have done till in today's lecture is given you an idea about how the minority current carrier behave in a p type base region, right. We also have come to the point how we have how a p-n junction works, and therefore how it can be translated into an NPN and a PNP transistor and its functionalities, right. So, we have understood all these things. When we meet tomorrow or next time when we meet, I will be discussing some mathematics about the current flow in a transistor which is carried off both drift and diffusion, and then see how we can optimize the functioning of an NPN and a PNP BJT. So, this is what we have learned today, and we will hope that you have understood a part of this work as far as this course is concerned. Thank you very much.